So we've divided the talk. I first want to thank so much the audience for being here. It's 1:30 a.m. and we have at least this half of the room packed. So the title of the talk, I'm actually going to talk about it during the talk, and what are we referring to in terms of evolving reality? So let's get started. And I want to start very simple. So data. What do we mean by data? And I think all of the 100 talks have data on them and they talk about data. Data is a collection of numbers or words. That's what it is. And so it's qualitative or quantitative. And it can come from many fields: scientific, cultural, financial, geographical. And there are many ways to generate data. One of the ways is through sensors. And through sensors, we typically collect data that is objective, quantifiable, numerical data. In my PhD thesis, for example, I put overhead cameras in a living environment, and these are the frustrums of the cameras, so the field of view. And then I used computer vision to compute where people are in the space and time, so on space and time. And I created visualizations that I put in the hands of architects to understand how space is being used, how space affords or limits certain behaviors. There's other types of data, for example, observations. And these data can be subjective and qualitative. Subjective means that there's somebody taking notes. There is a perspective, and it matters who this person is. Ethnography, for example, depends on the viewer, on the observer, on the taking of the notes, and on the analysis that you do on this data. One example is here in our visualization studio, where we have two students presenting a project on the large screen that we have there. The project is visualizing some data in some artistic way, and she's controlling the data and the visualization through her phone. So the students created a full system that allowed her to control what happens here on the large screen on the phone. And her teammate is taking notes of the reactions and questions and comments from the audience, which were the other students in the course. So learning to take qualitative data about their own projects is one of the lessons that they take from the visualization studios, from the courses in visualization itself. Another way to generate data is through mathematical models and computational simulations. For example, computational fluid dynamics. This is an example from Tina Weinkauf, another professor that works at the studio. And here, there's a model that shows us how fluids behave. And we're looking for things like swirling motions and vortices. Now, the big challenge is not generating data. We're actually doing a lot of that. The big challenge is the fact that most of the data that we're generating is unstructured. That is the largest challenge. And how do we deal with that? How do we make sense of so much unstructured data? And you can see here that it's going up pretty quickly. Mobile phones have turned humans into human sensors. We produce a constant stream of data of where we are, what we're doing, who we're meeting. It's like a digital exhaust. How do we deal with that? How do we benefit from that data? Those are some of the questions that we'd like to answer in the near future. And one way to do that is through visualization. What is visualization? What can it give us? So here's a famous set of 4 sets of numbers in 2 dimensions, x and y. It's from a British statistician. His name was Francis Anscombe. And he designed the sets to have exactly the same statistical features. The same mean across all 4 sets, the same variance, x-y correlation, and linear regression. So statistically, they're indistinguishable from each other. But let's take a look at them. Let's look at them a little closer. So here I graphed the first set. And you can see here's the linear correlation, and those are the x-y points, x-y coordinates. This is the second set. So even though they share exactly the same means, the numbers look very different once you graph them. The third set, you can take a look at the role of outliers. And the fourth set. So graphically, you can tell very quickly these are not the same numbers. So that's why we want to do visualization. This is a simple example that shows us how our eyes can detect patterns in data that we can't do when we have to read the numbers. When our eyes see colors and shapes and positions, it makes all the difference. Let me show you one of the recent examples that we developed at the studio together with Vinnova. This is an interactive visualization that you can view yourself online. Here's the address. So if you're going to take a photo, this is a good one right there. I've seen people taking photos all the time. And what do we do with this visualization? Well, first of all, let me tell you what the data is. The European Research Commission hands out money to do research, sometimes basic science, sometimes innovation. And they create frameworks every so often. Every 6-7 years, they create a new framework. The current framework is called Horizon 2020. And try to guess when it's going to end. 2020. It started in 2014, and so far they've given out 24 billion euros. By the end, they need to give out 80 billion euros. This is the largest funding scheme in European history. This is the future of humanity to some extent. This is where the money is going. So we want to know where the money is going, what projects are being funded, who's doing the research, what research. Horizon 2020 has 3 main pillars: societal challenges, excellent science, and industrial leadership, that are divided into objectives. So when you talk about societal challenges, and a lot of the talks, of the 100 talks in this marathon, are about this. They're about health and security and smart green technologies. And they are about food. When we talk about excellent science, typically researchers define the topic, and the money is given to an individual researcher to go deep in that topic. And there are different objectives and mechanisms to fund. And when we talk about industrial leadership, we're talking about information and communication technologies, we're talking about advanced manufacturing, and the text gets really small, but I hope you get the point. The idea is a group of people get together and they need to decide where they're going to put their money for everybody's future. This is terribly important. So with the interactive visualization online, you can go in and check how Sweden is doing. So Sweden has received funding for 664 projects. So now I'm not showing money, I'm showing number of projects. I'm showing a different thing in this Sankey tree. And you can see that KTH is on top with 122 projects. Karolinska second with 109, Lunds with 102. So this is nice. But what's even more interesting for me is this right here. Look how much larger the industrial leadership of KTH is compared to all the other universities in Sweden. And a lot of that funding is coming to our colleagues, the people that produce the data for the visualization studio through those simulations that I talked about. It is to fund the supercomputers that we have here at KTH. In fact, Beskov is the fastest supercomputer in Scandinavia currently. This changes every couple of years. So that's a lot of where the money is going. But so far I've been talking about flat screens. This is a flat screen. It's a front projection flat screen. This is an LCD flat screen once again with the visualization, and these are the students that created the visualization. It's always important to recognize the people that actually make the work happen. We just supervise it and give them cheerleading. And but we want to take it a little bit further. So I talked about data and visualizing data. Now let's talk about the evolving reality. And this is not an existential question. So what do we mean by evolving reality? Well, we actually mean the mixed reality spectrum. So now let me talk about this for a minute. I'm going to start here on the left talking about reality. And here's a mountain biker, and this is our view of that mountain biker. When we go out into the world and see this biker go downhill, that's what she looks like. And this, by the way, is the Olympic gold medalist in Rio 2016 from Sweden, Jenny Rissveds. And this is what she sees. If you put a camera on her, that's her first-person perspective of reality. You can see the perspective is this particular camera is somewhere in the chest. You can tell. It's not up in the head. Over here on the far right, we have virtual reality. And this fellow here is wearing a heads-up display. All right? How long he can wear this display before it fogs with sweat, it's a topic for another talk. This is a third-person perspective of the same biker as rendered from a virtual camera in the virtual environment of the virtual reality that this guy is doing. And this is the first-person perspective rendered from where his eyes are. Notice the difference between the two perspectives. But there are other points in the spectrum. Augmented reality is closer to reality, and what we want to do is put information into the real scene that is relevant and contextual. Where are you? Where are you going? How fast are you going? How fast are you pedaling? All right? And over here, this is what the biker would look like with the heads-up display that allows the biker to actually see the road, so there's nothing in the field of view, directly in the field of view. This is a little bit off the field of view, and here there's an artistic rendering of what the biker would see, which is closer to that. So this is an augmented reality biker. Now let's talk about augmented virtuality. That is taking real-world objects and scanning them to come into the virtual environment. And the real-world object that we're scanning now, and I'm going to show you a project that we created in the studio with a video, is the person itself. We're using a depth camera down here. Difficult to see in this projection, but you can see the light on the depth camera. And we're scanning the biker's feet, the skeleton, and how quickly the biker pedals is mapped to the speed of the virtual bike. And the orientation of the shoulders of the biker is mapped to the steering wheel of the bike. And notice that the biker is not wearing heads-up displays, but rather the screen in the studio is so large that it occupies the entire field of view of the biker. So sweat can dissipate. All right? So these are 4 points in the spectrum. There's one more that hardly ever gets talked about, and it is the real virtuality. That is, we give real objects virtual behavior. Some people call it UbiComp, ubiquitous computing, or pervasive computing. And there's one device that has had the greatest success in human history in terms of number of units sold and active. So I'll give you 2 seconds to think about it. And it's a real virtuality wallet, because this is my wallet, right? But on the other side of the wallet, there's a window into basically all of the knowledge and content that humanity has ever produced. So your wallet behaves virtually. It's a phone, it's a camera, it does so many things, and it accesses so much information. So this is another point in the spectrum. I want to talk about a project that my colleagues and I created called Braille Touch. Because believe it or not, blind people can get information from their phone by touching different places on the screen, and the screen reader tells them what they're touching. And if they want to activate something, they double tap it. So blind people can get a lot of information from the phone. In fact, they can take photos of things and send them, crowdsource it, and people online donate a little bit of their time and their site to put text to label what the picture is. So they take photos of labels, for example, of their medicine. Pretty cool. But to get information into the phone is very hard for blind people. So we basically transferred the functionality of a Braille keyboard into the phone. So it allows people to chord the text and put it into the phone. Now, Björn will talk about some of the challenges that we're facing when we go into this mixed reality spectrum.
Finally, I get a few minutes. I'm happy to do that. This part of the talk, we're going to focus on. There's so many challenges that people are currently working on. So this is just 3 examples of that. The first one being locomotion, how you move in these environments, creating objects, always an obstacle, and placing the objects in the physical world. So first for the locomotion. This is a very, very old picture where the first time we actually managed to map people's motions. That was Edwin Muybridge. Sorry about the misspelling there. He did that way back in 1887. In these worlds, how do we transfer the way we walk into these virtual worlds? The first and obvious thing was, of course, to map something on the floor, but then eventually you run out of floor and you run out of screen space. So now I'm out of frame. All of a sudden I'm back. Another way of doing that is to map these mechanical masterpieces where you can do endless walks on them, the omni walks, and there are a number of these different things. But they are pricey, and again you end up with very complicated things that might break in different ways. So then you can also move into the virtual world. And this is a very common principle that you do teleporting into the world. So you have some kind of digital tool within the world that you're currently working on. So you place a marker. In this case, it's this little circle, and you click on something, and then you suddenly move to that magical place. One of our students, Andreas Lin, he wanted to explore how you instead could use the eye tracking. You look at something, and then you walk there. So he implemented a headset or used with eye trackers. So you looked at something, and then you were magically moved there. So that at least took away these type of extra objects, so you could still be in the world. Another example of the challenge is to create these objects. 3D modelers, that's a skill. It's tedious and it's hard work to be a really, really good 3D modeler. And this student, Björn Thuresson, he's not a very good modeler. He's a good programmer and he's a good concept, but he's not a good modeler. So he wanted to, how can I get the objects that I want into my digital experiences? So he took one of these sort of current devices. This is a Tango device, and he wanted to use this. It's basically a phone, and he scanned objects. It was actually this particular object that he scanned, and that's the type of quality we sort of get now. We are not really there. It's not that you can immediately use that in your experience, but it's sort of getting there, and soon will be there. And another very different approach to that is by using markers. So here you have a big marker, and here you have another interactive marker. So you use a similar type of device, and when you move this device, it appears like that's your sketch tool. That in this case, it's starting to do a swirl, so you can do interactive sketching into this environment, and this is your viewing area of that environment. So it's a different type of approach, but you still try and how can we get these objects and the way we want them. And the third challenge is how can we place these objects? How can we get information about reality so we can start placing objects within that? Here we have an area which sort of looks like a typical startup, who knows? It's someone's basement somewhere. In this case, the student Kalle Stensson, he wanted to explore what are placeable areas, flat areas where you can put 2D content. He wanted an automatic real-time system that could detect these areas where that is possible. And here's where he currently got to. These green areas are these placeable areas, and the red ones, here you have the radiator, here you have the windows, not very good to place objects in. So that's one way of trying to get access to knowledge about the physical world. Another type of approach is geospace information. Here we have the future Nobel Museum, possibly. We'll see if that happens. Here's a model of that, and here it's at its actual location. So this is, imagine that you look at something again through a device like this. But here you have the problem of occlusion. It knows its position, so it's the correct location, but it doesn't know its environment. So here it has to include information about the surrounding buildings, so you can map it into the 3D environment and not in the 2D environment. So that's sort of where we currently are, and that are some of the examples that our students, the future, are trying to explore in these areas. And here you have some examples of that. Here we have Adrian, here we have Andreas, and some others. Thank you so much.
Thank you.